Hello everyone. We're going to take a step back. I skipped this section initially after we took the test because I wasn't 100% sure how I was going to go about teaching it to you guys. It's not a super difficult section. It's a section that's built more around your perception and your observation skills than really on your math skills. So it's going to have a little bit of a different feel to it. This is section 4.1. Out of the textbook. The last section we did was 4.2, which was over isosceles and equilateral triangles. 4.1 is over a concept called congruence, which is a word we've thrown around a little bit in class already, and I want to make sure you guys have a solid understanding of kind of where we go with it. There's no formulas for this one. There's actually very little math or actual arithmetic with this section. A big part of this section is really going to be built around you guys using prior results that we have from other sections to not really prove anything. This really isn't a proving section, but really to deduce whether objects are congruent or not. So the first thing we need to start off with here is some vocab. The first piece of vocab we're going to have here is going to be, what is a rigid motion? Okay, we already have this concept from our previous class, or from previous classes. We already defined this concept. A rigid motion is any transformation, so any shift or flip that we can do with an object. It's any transformation that maintains angle measures and side lengths. And side lengths. So that's a rigid motion. That's going to be our first piece of vocab. It's something we already know, but we're just going to take another look at it there. The next thing we have here is going to be this concept of congruence. The textbook has a definition for this. I'll give you guys my definition for our purposes here, just to kind of clean up the concept. Congruence is basically it's when you have two objects that other than orientation, so the way that the object is positioned, or whether it's flipped over or not, it's objects that it's when objects have the same angles and side lengths. Okay, so we have this concept of a rigid motion where, let me see if I can grab my protractor or something. Oh, I know what I'm going to use. Here we go. Hold on. Alright, here we go. The book actually does this too, so we're going to use this example too. Okay, so a dollar bill. Okay, cool. So the idea is that a rigid motion is when we take an object and regardless of how we move it or if we flip it over or anything like that, we're using this really just as a rectangle, so don't think of this as a dollar bill. Don't concentrate too much on like markings and stuff. That's not the point here. This is really ultimately a rectangle. We rotate it 90 degrees, it's still a rectangle. Okay, so this, actually let me grab you another dollar bill. Hold on. For our purposes, we're going to assume that dollar bills all have the same dimensions. So we have our original dollar bill, and we have a new dollar bill. So these two objects, oriented differently right now, but ultimately the same shape. So they're both this rectangle, just one of them's rotated slightly, or one of them might be rotated and then flipped over, sort of thing. So we can have compositions here. So a rigid motion is any transformation that leads to us being able to, or leads to a manipulation of a given object. Whereas a congruence is when we have two objects that have the same measurements, that have the same angles. So a rigid motion leads to congruent objects. That is really the big takeaway for this section, is that a rigid motion generates congruent objects. You should write that down. Yes. All right. Good. So, that's really it. That's pretty much the entire video. I want to give you guys so the way that the homework or the book assignment for this particular section is going to work. You're going to be given different objects, and they're going to ask you they're going to ask you to determine if they're congruent objects, or they're going to give you a transformation, which could be a composite transformation. Always remember that whenever we have composed transformations, so when we have a composition of transformations, that's the little circle between transformations. So for example, if we have a translation of some sort followed by a rotation of some sort, so we have some sort of an angle measurement and some sort of a point that we go around of a given object. Okay. Always remember that with these things, we always read these going right to left. Always read these things, read right to left. That's going that way. Okay, remember that. So we always read these things going right to left. Tighten that up a little bit for you guys. There we go. Okay, so always read these going right to left. Let's see, what else do you need to know in order to do this? So you're going to see problems where they give you two objects and they ask you to determine if there is determine a composition of functions, or a composition of transformations that will generate two objects. So for example here, I'm given this original dollar bill, and then I'm given say, this dollar bill, and they're looking for what transformation generates that. Well, we have a line of reflection that goes right here. Another way of thinking of this is this could be a rotation around a given point. You could do a composition. There's several ways for us to generate this particular rotation. Your job is going to be to find a composite or just a direct transformation that leads to that. That'll be one of them. The other one that you'll be given is you'll be asked to find the transformation. The other thing you'll be asked to do is confirm or verify whether two objects are congruent or not. That comes in a couple of different ways. Remember that congruent objects will have the same angles, and they will also have the same side lengths. Okay, so now comes the question of how do we determine these things? So I'm trying to remember the questions that I believe I've sent you. I don't think you guys have to worry about the same angle scenario, but you do need to worry about the same side length scenario. To do that in the coordinate plane, you will need the distance formula. So if you don't remember that, that's x1 minus x2 quantity squared plus y1 plus, which would be y1 minus y2, all square rooted. Okay, so let me get rid of that. That should be a plus. There we go. So y1 minus y2. Okay, so you guys have the distance formula. You have your protractor if you do need to measure a same angle scenario to determine if those are congruent objects or not. The other thing, and this actually isn't in the book, but it's this concept of orientation. It's orientation of points, or distribution of points, I guess is a better way to describe it, orientation of points. To explain that, if I have a square, and I label this point A, this point B, this point C, and this point D, and then I give you another square, and I have it labeled as A, and let's do C, and we'll do B, and we'll do D here. And you're asked to determine the translation that creates this, or determine the rigid motion that would create this. There really isn't anything that does this, because you'll notice here that A is diagonal from C, but A is no longer diagonal from C, which means this is a transformation that can't happen. That's orientation of points. So when you're doing reflections or rotations or translations, orientation of points, or the layout of the object, that has to remain constant. So if you have a weird distribution of the letters on here that doesn't really match up with the layout of the points on your original object, that should signal some red flags in your head. It's like, this isn't going to work. So like in this case, A is diagonal to C, A is no longer diagonal to C. It's like there really isn't a transformation that makes that happen. So this would be an example of non-congruent objects, because it's like that didn't happen when we first did this. Let's see, what else can I throw your way? That's pretty much it. Oh, one more piece of vocabulary you guys are going to see. Sometimes rigid motions are called a congruence You'll see this in the book assignment. It's sometimes called a congruence transformation, because a rigid motion takes an object, does something to it, manipulates it in some way, and orients it in a different way, but it maintains angles and side lengths, which is exactly what congruent objects are. So rigid motions are also sometimes called congruence transformations. Let's see, what else do you guys need to know here? That's pretty much it. I did want to give you guys just it's just kind of running through our three transformations again. We have the reflection, we have the translation, and we have the rotation. So I was just going to give you a little kind of cheat sheet to go along with this. So if I have a triangle and I reflect it, okay, one thing you're going to notice here is that because we're always flipping over horizontal or vertical lines, the position of the object in terms of its height off the y-axis, so like the vertical height here, the height or the width of it, or however you want to look at it, the position is roughly going to be the same, but in a different quadrant. But the orientation of the points are going to change. Okay, so when you flip an object over, or you flip an object over across the x or y axis, so like if I take a dollar bill here, so if I flip this over a line here, all of my points, the points that were originally here, are now on this side. So if you think of it this way, these 2 points here, when I flip an object horizontally, are actually now these points over here. So our orientation is going to change, but our position is roughly going to be in the same spot, because we're still, when we flip horizontally, all we do is we bounce from one quadrant to the next quadrant, or if we go this way, we go this way. So your orientation, your x coordinates are either going to stay the same, or your y coordinates are going to stay the same, depending upon which way you're flipping. That's the takeaway I'm trying to get you guys to see there. With translations, the orientation or the orientation of points does not change. So take that here. So the orientation of points for a translation does not change. So if this is A, this is B, this is C, and this is D here, when we slide that object around, those points never change regardless of the new object. Those will always be where A, B, C, and D are. So the orientation of points is always preserved with a translation. With a rotation, because we're rotating around a point, the way I always think of it is there's going to be one edge, or there's going to be part of our object, whatever it happens to be, whether it's a vertex or a side length or something, that is always going to be facing towards an object. So the orientation of points isn't going to change. You're always going to see the orientation of points around the object in the same order. Those change with reflections. The orientation of points changes with the reflection. The orientation is not going to change, but the position in the coordinate plane is going to change. So your orientation of points will always will always stay the same, but your position in the coordinate plane will change with a rotation. So those are things that you can look out for when you're doing this one. You've seen some of these problems on quizzes and on the homeworks already. A lot of you have kind of an intuitive sense of what's going to be, what I'm trying to explain here. You're going to see it happen. This is one where I really think it helps for you guys to sit down and just do it, and then if there's gaps in your understanding, I can help you guys out with it during class and stuff. This one's not too hard. It's largely vocabulary is all that should be on your note sheet, and then some random stuff here. You will need the distance formula if you guys don't remember it in order to move on to the next part. There'll be questions, I'm sure. If you guys have any questions, just make sure you bring them up to me in class, and we'll go forward from there. All right, I'll see you guys tomorrow.